Hello, I'm Miss Ginsburg with KnowAtom, and today we're going to be reading Satellites. This is a lab manual in Unit 3. Section 1, Earth's Place in Space. Communicating with Satellites. In 2010, a major earthquake hit Haiti. It was so powerful that it affected about 3 million people. It damaged or destroyed thousands of buildings. Many people from around the world came to Haiti to help the country recover from the earthquake. One challenge after a major disaster is that much of the infrastructure is often damaged. Infrastructure refers to the physical structures and facilities that help a society or organization function. For example, the earthquake in Haiti destroyed many cellular towers. This made it almost impossible to use cell phones in the days right after the earthquake. Satellite phones. Many international groups use satellite phones to communicate when they couldn't use cell phones. Satellite phones don't rely on cell towers or other infrastructure on land. Instead, they use satellites that are orbiting Earth. To orbit means to move around another object in a complete path, such as a circle or an oval. The satellite phone uses those satellites in space to send information rather than cellular towers. Using satellites helps people who wanted to coordinate the delivery of important goods, including blankets and plastic sheeting that people could use for shelter. Orbiting in space. There are thousands of satellites currently orbiting Earth. A satellite is a body that orbits another body in space. The moon is a natural satellite that orbits Earth. The satellites used by satellite phones are artificial because they are made by humans. Both natural and artificial satellites orbit Earth because of gravity and inertia. Remember that gravity is the force of attraction between all matter, and that Earth is so massive that its gravitational field extends beyond the atmosphere, pulling on all objects within it. Earth's gravity. The force of Earth's gravity doesn't pull the moon or the other satellites down to Earth's surface. This is because all objects in orbit are also moving sideways. For example, the moon moves at a speed of 3,683 kilometers per hour. If Earth's gravitational field didn't exist, all satellites would travel in a straight line because of inertia. Inertia is the tendency of an object at rest to remain at rest, and an object in motion to remain in motion unless acted on by an outside force. If a ball is at rest on the ground, it will not suddenly start moving on its own. It needs an outside force, such as you kicking it, to cause it to move. Similarly, once the ball starts moving, it will continue moving forever if no other forces act on it. However, here on Earth, both friction and air resistance eventually cause the ball to slow down by transferring energy out of it. In space, Earth's gravity provides the outside force that changes the motion of its satellites. Without it, the moon and other satellites would speed through empty space in a straight line. However, Earth's gravitational field is so strong that its attractive force pulls on the satellites as they move. For an object to remain in orbit, its speed must be balanced by the pull of gravity. If its speed is too slow, it will fall back to Earth. If it is too fast, it will fly off in a straight line in space. This is similar to the motion of a ball on a string. If you swing the string around, the ball is constantly being pulled toward your hand. This is similar to how Earth's gravity pulls the moon and other satellites toward it. But the ball's sideways motion around the string keeps it moving, so it doesn't fall to the center. Without that pull to the center, for example, if you let go of the string, the ball would go flying off into a straight line away from you. Satellites orbit at different speeds and different distances from Earth. Some satellites are geostationary. These satellites travel from west to east over the equator. They are called geostationary because they move in the same direction and at the same speed as Earth. As a result, it appears from Earth as though they don't move because they are always above the same spot on Earth. Moon-Earth-Sun system. Each of the satellites orbiting Earth form a system made up of them and Earth. For example, Earth and the Moon form an Earth-Moon system. They form a system because they are connected, interacting parts that make up a more complex whole. At the same time as the satellites orbit Earth, Earth itself is in motion, orbiting the Sun. The Sun is a star at the center of a solar system. A solar system is a collection of planets and other objects that orbit a sun. A planet is a body that orbits the sun, is massive enough for its own gravity to make it round, and has cleared out smaller objects around its orbit. There are currently 8 known planets in our solar system: Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune. Earth and all of the other planets are themselves satellites because they orbit the sun. The sun. All of the planets orbit the sun for the same reason that satellites orbit Earth: gravity and inertia. The sun is so much more massive than Earth that its gravitational field pulls Earth and the other planets into orbit around it. The sun plays another important role on Earth. It provides energy to the planet in the forms of light and heat. It does this through exothermic reactions that take place deep within the sun's interior. Remember that exothermic reactions are chemical reactions in which energy is released into the environment. The light and heat produced by the sun are evidence of these exothermic reactions. That energy is transferred to Earth through radiation. Radiation is heat transfer that occurs without contact between the heat source and the object heated. We'll explore radiation more in the next lesson. As the sun shines, it lights up Earth. However, Earth is also rotating or spinning once every 23 hours and 56 minutes. As it rotates, the sun lights up half of the planet at a time. This is day and night on Earth. Throughout the year, different parts of the planet experience variations in the number of hours of daylight compared to night by the length of one complete day, but the length of one complete day is always 23 hours and 56 minutes. The sun also lights up the moon. The moon doesn't emit its own light. Instead, we see the moon because the sun shines on it, lighting it up for us. This is possible because the moon reflects the sunlight. The light bounces off of the moon and then travels to Earth. The lit part of the moon that we see from Earth depends on the moon's position in space relative to Earth and the sun. The moon's position in the solar system. Let's explore the moon's position in the solar system a little more. You may have heard of the dark side of the moon. This phrase came about because here on Earth, the same side of the moon is always facing Earth. However, it isn't true that the side of the moon facing away from Earth is always dark. Just like on Earth, half of the moon gets light and then dark as the moon rotates. If the moon didn't rotate at all, we would see both sides of the moon as it orbited Earth. However, the same side of the moon always faces Earth because it takes the moon about the same amount of time to complete one rotation as it does to complete one orbit around Earth. The moon completes one rotation and one orbit around Earth in approximately 29 days. Because both of these motions take the same amount of time, the same side of the moon always faces Earth. The moon cycles. As the moon travels around Earth over the course of a month, it appears to change from a full white disk in the sky to a small silver and then back to a full white disk, a small sliver. These changes are called phases. There are 8 phases in the moon cycle, which describes the changing appearance of the moon as seen from Earth as it orbits Earth. The moon cycle occurs because of how the sun's light reflects off of the moon and back to Earth. It changes over the course of a month because the moon changes its location in space as it orbits Earth. For example, new moon is the first phase of the moon cycle. It occurs when the moon is positioned between Earth and the sun. Because the moon is in between the sun and Earth, the entire half of the moon lit by the sun is facing away from Earth, so the moon is not visible from Earth. As the moon continues its orbit, the amount of sunlight reflected off of the moon and back to Earth changes. The part of the moon lit by the sun increases, but it is still less than half. This is the waxing crescent phase of the moon cycle. As the moon continues its orbit, it reaches a point where it is at 90-degree angle relative to Earth and the sun. This is the first quarter of the moon cycle. From the northern hemisphere, the left half of the moon appears unlit and the right half of the moon appears lit. After the first quarter, the sunlit part of the moon continues to increase. This is called the waxing gibbous phase of the moon cycle. When the moon reaches the opposite side of Earth, we see a full moon from Earth, where it appears round and bright. The moon, Earth, and the sun are lined up similarly to new moon, but the moon is on the opposite side of Earth. As a result, the entire half of the moon that receives sunlight is facing Earth. After full moon, the sunlit part of the moon begins to decrease. The waning gibbous phase occurs when more than half of the moon is lit by the sun, but the lit part is decreasing. As the moon continues its orbit, it again reaches a point where it is at a 90-degree angle relative to Earth and the sun. This is the third quarter. From the northern hemisphere, the left half of the moon appears lit and the right half of the moon appears unlit. Following the third quarter is the waning crescent, which wanes until the light is completely gone, beginning the cycle again with new moon. Depending on the moon's exact position in its orbit, it can sometimes block the sun's light from reaching Earth. This results in a solar eclipse. An eclipse occurs when one object in the solar system moves into the shadow of another object. In a solar eclipse, the moon moves between the sun and Earth. If the moon's shadow falls on Earth during new moon, it appears that the sun has become completely dark. Solar eclipses do not happen every month. This is because the moon's orbit around Earth is tilted 5 degrees. As a result, the alignment of Earth, the moon, and sun only occur about once every 6 months. A partial solar eclipse happens when the sun, moon, and Earth are not exactly lined up. The sun appears to have a dark shadow on only a small part of its surface. For a total eclipse to take place, the sun, moon, and Earth must be in a direct line. During full moon, a lunar eclipse can sometimes occur. In contrast to solar eclipses, lunar eclipses occur when Earth moves between the sun and the moon. During a lunar eclipse, Earth blocks the sun's light that normally reflects off of the moon. Lunar eclipses can only occur during the full moon when the moon passes through Earth's shadow. The moon does not completely disappear during a lunar eclipse. Instead, it appears reddish. This is because light from the sun must first pass through a long and dense layer of the Earth's atmosphere before it reaches the moon. Just like the solar eclipse, lunar eclipses do not occur every full moon. Satellites in the solar system. Our moon isn't the only moon in the solar system. Other planets also have moons. There are more than 170 known moons in the solar system. It is likely that scientists will continue to find more. Like all satellites, these moons orbit a planet when that planet's gravity is strong enough to change their motion by pulling on them. Scientists on Earth have also launched artificial satellites into orbit around other planets. They want to gather data about those planets. Some of the satellites orbiting Earth are also gathering data on the rest of the solar system. Planets and their satellites. The more massive a planet is, the more satellites it can hold in its orbit. This is because the more massive an object is, the more its gravity will pull on other objects. For example, Jupiter is the 5th planet from the Sun. Jupiter has so much mass that it holds in orbit the most moons of any planet. Jupiter is so large that all of the other planets in the solar system could fit inside it. More than 1,000 Earths could fit inside Jupiter. Every planet in the solar system, including Earth and Jupiter, is held in its orbit by the force of the sun's gravity. In addition to planets, the sun is also orbited by non-planets. The asteroid belt between Mars and Jupiter is made up of rocks left over from planets that didn't form. Comets are small objects made up of mostly ice and dust, and they are usually found farther from the sun. Planet-like masses, called dwarf planets, are also found throughout our solar system. Moons orbit planets and not the sun because the force of gravity becomes weaker as the distance between two objects increases. For example, Earth's moon is much closer to Earth than it is to the sun, so Earth's gravity is the dominant force on it. This is also why we all experience the downward pull of Earth's gravity. A moving universe. Just as the 8 known planets of our solar system orbit the sun, our entire solar system orbits the center of the Milky Way galaxy. Galaxies are large clusters of stars held together by gravity. The Milky Way galaxy is shaped like a thick pancake. It contains more than 200 billion stars, including our sun. Just like in the solar system, there are vast stretches of empty space within the galaxy. We live near the edge of the Milky Way galaxy. It gets its name because it looks faint and white in the sky, similar to spilled milk. On a very dark night, you may be able to see the Milky Way as a thick band of stars. Our entire solar system is in motion for the same reason that the moon orbits Earth and the moon-Earth system orbits the sun. The center of the Milky Way galaxy has a much larger mass than our solar system or the other stars and systems within the galaxy. So its gravitational force pulls all of the stars within the galaxy into orbit around it. And the Milky Way galaxy is just one of about 100 billion galaxies in the universe. The universe is the wide open space that holds all matter and energy known to exist. Section 2. Waves transfer information. Using satellites to navigate. Turn left and then continue straight. If you've ever used a smartphone or a car's navigation system, you have communicated with satellites orbiting about 20,000 kilometers or 12,600 miles above Earth's surface. The best known navigation satellites in the United States are part of GPS, which stands for the Global Positioning System. GPS works by using 24 satellites that orbit Earth once every 12 hours. These satellites send information about a location that can tell us exactly where we are. Waves. To understand how satellites far above Earth can provide your exact location on the ground, it helps to understand waves. A wave is a disturbance that travels through space and/or matter, transferring energy as it moves. People can use waves in a variety of ways, including in GPS, cell phones, radio, microwaves, and CDs. Most waves fall into one of two categories: light waves, also called electromagnetic waves, and mechanical waves. We'll explore how waves are disturbances and the differences and similarities between the two categories of waves. Waves and matter. Picture a slinky. If you stretch the slinky out from end to end and then move the first coil up and down or from side to side, a wave will travel from that end of the slinky to the other end. The waves in a slinky are mechanical waves because they are caused by vibrations in matter. Remember that matter is anything that has mass and takes up space. This matter is called a medium, and it can be a solid, a liquid, or a gas. For example, rock is a solid medium, as is a slinky. Water is a liquid medium, and air is a gaseous medium. As mechanical waves travel through a medium, they cause molecules within the matter to bump into each other. As this happens, energy transfers from one molecule to the next. It is important to note that waves don't carry matter. After the energy moves through, each coil of the slinky will return to its original position. Another common mechanical wave is caused by raindrops on a still lake. The kinetic energy of the falling rain transfers to the water, which creates water waves that carry that energy as they ripple outward. Once the ripples die down, the water returns to the same position. Sound waves are another form of mechanical waves. Picture a person blowing into a trumpet. The energy of the person's exhalation causes nearby air molecules to vibrate and bump into the molecules closest to them. This contact passes on the energy and makes them vibrate too. Then those molecules bump into more particles and so on. Particles stop vibrating once they have passed on the energy. Light waves. Unlike mechanical waves, light waves do not need a medium to travel. A light wave is a pattern of light energy that moves at a constant speed until meeting matter. Remember that the sun transfers energy to Earth through radiation, heat transfer that occurs without contact between the heat source and the object heated. That energy travels to Earth in light waves. Exactly how light waves travel is very complex, and scientists have many unanswered questions. However, scientists do know that light waves can travel through a vacuum because the sun's light reaches Earth through the vacuum of space. A vacuum is a space that has no matter in it. In contrast, sound cannot travel through the vacuum of space because there are vast empty regions between matter in space, which means that molecules are too far apart to transmit the energy. There are many kinds of light energy. Microwaves are used in appliances to heat up your food and in satellites for communication and navigation. X-rays are used at the dentist to capture images of teeth and at the airport to see through bags. The type of light energy depends on the amount of energy in the different waves. Radio waves have the lowest energy. Your radio captures radio waves that are sent out by radio stations. As waves move, they create a disturbance. This is true for both mechanical waves and light waves. Picture the pebble being thrown in the lake. The waves ripple outward, creating a disturbance in the water. However, not all waves create a disturbance that moves in the same direction. For example, in some waves, the disturbance moves perpendicular to the direction of the wave itself. In other words, if the wave moves from left to right, the disturbance moves up and down. This kind of wave is called a transverse wave. When a crowd of people in a stadium do the wave, they are modeling a transverse wave. The individual people move up and down while the wave moves from left to right or right to left. This is another example of how waves move energy, not matter. After the disturbance passes through, the people go back to where they were before the wave moved through. Light waves are also transverse waves. Longitudinal waves. In some waves, the disturbance moves parallel to the direction of the wave itself. If the wave moves from left to right, the disturbance also moves from left to right. This kind of wave is called a longitudinal wave. Sound waves are longitudinal. As sound waves move through a medium, the molecules of the medium collide with one another in the same direction the sound wave is moving. Patterns in waves. All waves represent repeating patterns. This can be understood by thinking about the anatomy of a simple wave. The wavelength is the distance spanned by one cycle of the motion of the wave. In transverse waves, it is usually measured as the distance between two crests, the top of the wave, or two troughs, the bottom of the wave. In longitudinal waves, it is measured as the distance between compressions, point where the molecules are pressed together, or rarefactions, point where the molecules spread out. Amplitude and frequency. The amplitude is a measure of the wave's displacement from its resting position. For example, in a water wave, its amplitude is its height above the water's surface. In a mechanical wave, the amplitude is proportional to the amount of energy carried. This means that if the amplitude of a mechanical wave is doubled, each wave will have 4 times as much energy. In a light wave, the amplitude is related to its intensity, which we see as brightness. A light wave with a higher amplitude will be brighter than a light wave with a lower amplitude. The frequency of a wave is the number of waves that passed a set point in a given amount of time. A wave with a greater frequency also has a shorter wavelength. If you look at the electromagnetic spectrum diagram on page 22, you'll notice this pattern. Radio waves and microwaves have long wavelengths and low frequencies. X-rays and gamma rays have short wavelengths and high frequencies. Waves that have low frequencies and long wavelengths carry less energy than waves with high frequencies and short wavelengths. Remember that radio waves have the least energy of all electromagnetic waves. Waves interact with matter. As waves move through space or matter, they continue in a straight line until they come into contact with a different medium, which changes their motion. There are different ways that a wave can behave after this interaction, but we're going to focus on the 3 main ones: reflection, absorption, and transmission. A wave is reflected when it encounters a substance that acts as a barrier. Light that is fully reflected will bounce off of the substance and back into your eyes. This is what happens when you look in a mirror. Your image is reflected back. That happens because light has reflected off of the mirror and back into your eyes. This is also how we are able to see the moon. The sun's light reflects off of the moon's surface and into our eyes on Earth. A wave is absorbed when it hits a substance and causes the molecules of that substance to vibrate and move. This causes energy to be transferred away from the wave because it has been absorbed by the substance. Light that is fully absorbed will transform into another form of energy, usually thermal energy, which we feel as heat. The more an object's molecules move and vibrate, the hotter it becomes. This is why black objects become hotter than lighter objects. Black objects absorb all light waves and convert them into thermal energy. Finally, light is transmitted when it moves through a substance. Transparent materials, such as glass, transmit light. This is why you can see through them. How light behaves depends on the medium with which it is interacting. Some materials are more reflective or absorptive than others. It is because of this that we see the world in the colors that we do. A small band of electromagnetic spectrum is made up of visible light. Visible light is all of the light waves our eyes can see. Each color is determined by its specific frequency and wavelength. Color of an object. An object's color is not within the object itself. Instead, the color of an object is determined by how that object interacts with light and then reflects, absorbs, or transmits it. When visible light hits an object, different frequencies are absorbed and reflected. For example, a strawberry is red because it absorbs all of the frequencies of visible light that shine on it except for the frequency associated with red. Black and white are not actually colors because they don't have a specific wavelength. Black objects absorb all wavelengths of light and convert them into heat. In contrast, white objects reflect all wavelengths of light. As waves interact with matter, their properties can change. For example, as light moves from one medium to another, the wave can become bent. This is called refraction. Refraction occurs because light travels more slowly in air than it does in the vacuum of space. It moves even more slowly in water than it does in air. When a wave is refracted, its speed changes, as does its wavelength. However, its frequency remains the same. Refraction is what happens when you look at an object that is partly in water and partly in air. The object appears bent at the water's surface because light waves are bending at the boundary between the air medium and the water medium. Rainbows. Rainbows are a result of light being refracted and then reflected by water droplets. Rainbows can occur whenever there are water droplets in the air. As the sun's rays hits a water droplet, some of the light is reflected. Some of it is transmitted through the water drop. The transmitted light refracts or bends at the surface of the water droplets. When this refracted light hits the back of the water droplet, some of it is reflected and travels back to the surface again. Here, some of the light is reflected back into the water droplet. The rest is transmitted into the air as it exits the drop. The degree that the light wave is refracted depends upon its frequency, which determines its color. This is why rainbows form the arc of colored bands in the way that they do. Sending and receiving information. Visible light is a small portion of the entire electromagnetic spectrum. For example, music played on the radio is sent through light waves from a radio station to your radio. These light waves are radio waves, so they have low frequencies and long wavelengths. They work well for transmitting songs on the radio because radio waves can be transmitted through most materials, including walls and doors. Each radio station has its own frequency, so its transmissions are separate from everyone else's. Earth's upper atmosphere reflects radio waves, so they cannot be transmitted beyond this layer into space. For this reason, satellites send microwaves. Microwaves have shorter wavelengths and higher frequencies than radio waves. Microwaves are useful because they are not reflected by Earth's atmosphere. Because of this, microwaves can be transmitted from space to the ground. However, they are reflected by metal and tall buildings. This is why it can be hard to use GPS in the middle of a city where you are surrounded by tall buildings. The GPS network involves more than just its satellite because GPS is a communication system. A communication system is a group of interacting components that function together to transmit or exchange information between people and equipment. Radio stations are also part of a communication system made up of the radio station, antennae, and radios. Analog versus digital. All communication systems begin with a transmitter. This transmitter sends information. For example, navigation satellites orbiting Earth transmit microwaves that travel at the speed of light in all directions. In order for people on Earth to receive the information sent by the satellites, GPS must also include receivers that pick up those microwaves. There are many different kinds of receivers. For example, many phones and cars have a GPS receiver in them. These receivers are constantly listening for a signal from the satellite. Once they receive a signal from 3 different satellites, they can calculate your location. Communication signals. GPS and many other technologies use 2 different kinds of signals to communicate, analog and digital. In both technologies, information is sent from one device and received by another device. The difference is in how the information is captured, stored, and then sent on. In analog technology, the information is recorded or used in its original form. In digital technology, the information is translated into a numerical value. Those numerical values are sent as wave pulses. For example, a GPS receiver receives an analog signal. This means it receives a microwave carrying a replica of the original wave sent by the satellite. In digital technology, the information is translated into a numerical value, usually various combinations of ones and zeros. Those numerical values are sent as wave pulses. Digital signals are more reliable than analog. This is because the recording does not become less precise over time. As long as the numbers can be read, you will always get exactly the same wave. Compare 2 simple phone calls. One of the calls uses just analog signals. The other one converts analog signals to digital. We'll start with the analog to digital phone call. If you're talking on the phone, your voice produces an analog signal in the form of a sound wave. That sound wave enters the phone. There, it is converted to a digital signal. This signal is made up of pulses of ones and zeros. The digital signal is sent through microwaves in a cell tower, which sends the message to a satellite orbiting Earth. The satellite sends the signal back to another cell tower on Earth. The signal then moves to the phone of the person receiving the call. At this point, the digital signal is changed back into an analog signal in the form of sound waves. These sound waves are what the person on the other end hears. As the signal travels, it picks up a lot of noise. This is called interference. However, because the sound wave was broken down into discrete numbers, the phone can easily convert the sound wave back to the same pattern as the original signal. Analog signals. Now, let's contrast that call to one that uses just analog signals. Just like with the digital call, the original analog signal is sent into phone in the form of sound waves from your voice. Then, instead of being converted to digital, it is sent through wires as an analog wave. There are pros and cons to both analog and digital when it comes to making phone calls. For example, analog phone calls have been around for much longer, and they are cheaper. However, digital calls are more secure because the digital code encrypts the conversation, so outside listeners cannot follow what is being said. What is a laser? Lasers are found in many different applications. They are used in CD and DVD players. Doctors use lasers for some kinds of surgery, including eye surgery. Lasers can also be used by metal workers to cut metal and workers in factories to cut cloth. So what exactly are lasers? They are a special form of light created by humans. Natural light is made up of many different wavelengths and frequencies of light waves. Unlike natural light, lasers use just one wavelength. For example, a red laser uses just the wavelength and frequency associated with the color red. Another important difference between the light in a laser and ordinary light is that all of the crests and troughs of the wave line up. Scientists call this coherent. The final difference between ordinary light and the light in a laser is that the light in a laser is very concentrated. Unlike ordinary light, which spreads out in all directions, the light waves in a laser all travel in the same direction, exactly parallel to one another. This is why the light from a laser can be concentrated on one spot. Section 3. Engineering insulation. Wearing a spacesuit. The International Space Station is an artificial satellite in orbit around Earth. It is not just any satellite, however. The space station is a moving science laboratory that orbits 386 kilometers or 240 miles above Earth. Astronauts from many different countries live on board the space station. Sometimes astronauts go on spacewalks around outside of the space station. They do this to make repairs to the space station or to other artificial satellites in orbit around Earth. Suiting up. Before they do this, they have to suit up. An astronaut's spacesuit is complex. It has many different parts. It is actually a personalized spacecraft. It is designed to protect the astronaut in the harsh space environment. There are many reasons astronauts need to wear spacesuits. One reason is that there is no atmosphere in space. This means there is no oxygen for people to breathe. Oxygen is essential for life, so the spacesuit has an oxygen tank built into it. The spacesuit also has a radio, earphones, and microphones. This lets the astronaut talk to other astronauts back on board the space station. Thermal energy transfer. Insulation is also very important in space. The side of the astronaut facing the sun may be heated to temperatures as high as 121 degrees Celsius or 250 degrees Fahrenheit. The side of the astronaut facing away from the sun may reach temperatures as low as negative 156 degrees Celsius or negative 250 degrees Fahrenheit. Because of this, the spacesuit is designed with very specific materials that help to regulate the astronaut's temperature. There are 14 layers that make up the spacesuit arm. 7 of these layers are for insulation. They make the spacesuit act like a thermos. They keep the temperatures inside the suit within a comfortable range. Heat transfer. In order to understand how materials can provide insulation, it is important to understand how heat transfers between substances. Remember that energy can transfer into or out of systems or objects. This is an important concept because energy is never created or destroyed. Heat is thermal energy that has transferred whenever two substances are at different temperatures. Temperature is a measure of heat. It is measured in Celsius with a thermometer. Heat always flows from faster moving atoms, a higher temperature, to slower moving atoms, a cooler temperature, until both substances reach the same temperature. This point is called equilibrium. Here on Earth, thermal energy transfers is in one of three ways: radiation, conduction, or convection. We'll explore convection more later on in the year because it only occurs in liquids and gases, so it does not occur in space. In this unit, we'll focus on radiation and conduction, which both occur in space. Radiation is the primary way that heat is transferred in space because there's so much empty space. Radiation is the only form of heat transfer that doesn't require contact between the heat source and the object heated. As the sun produces light and heat through chemical reactions, it transfers that energy to Earth, the moon, and all other objects in the solar system through radiation. Radiation is what causes the side of the astronaut facing the sun to reach 121 degrees Celsius. On occasion, heat can also transfer through conduction in space. Conduction is a form of heat transfer that occurs when molecules collide. On Earth, it occurs all of the time. For example, if you pour a hot beverage into a mug, heat is transferred through conduction from the hot beverage to the cooler mug and then to your hand. When an astronaut is in space, conduction occurs between the astronaut and any surface the astronaut comes into contact with. This includes satellites or other objects the astronaut is working on. Engineering for temperatures in space. The goal of insulation is to reduce the amount of heat transfer that occurs. The spacesuit uses many different kinds of insulating materials. Each material is chosen deliberately by engineers. Remember that scientists use experiments to gain knowledge, while engineers use that scientific knowledge and mathematics to solve problems by creating new technologies. A technology is not just a computer or electronic device. Instead, it is anything that people have modified from the natural world to meet their needs and wants. Similar to how scientists follow a scientific process to answer a question, engineers also follow a process. Engineers often follow a process with 8 steps that guides them as they create new technologies to solve problems. The engineering process is similar to the scientific process, but it differs because each has a different goal. Scientists are trying to answer a question, while engineers are trying to solve a problem. The engineering process begins with a problem. When engineers are defining a problem, they include the criteria, the needs the solution must meet, and constraints, ways the solution is limited. For example, engineers designing the spacesuit were working on the problem of how to keep astronauts safe in the harsh space environment. In this example, the criteria might be that the materials have to be able to withstand the extreme heat and cold of space. Available materials and cost are two common engineering constraints. However, engineers designing spacesuits for astronauts are less worried about cost than many engineers because safety is the primary concern. According to some estimates, one spacesuit cost about $2 million. Once they have identified the problem, engineers research it to find out what is already known. In our example, engineers would need to know about heat transfer. They would also need to know how the sun's energy transfers heat through radiation. And they would need to know that certain materials are more reflective than others, while others are more absorbent. More absorbent materials convert the sun's energy into heat. Some materials are also good thermal conductors. This means they easily let heat pass through them. Metals are good thermal conductors. Materials that are good thermal insulators do not easily let heat pass through them. Plastics and foams are good thermal insulators. Before engineers begin designing a solution, they survey the available materials. This survey includes a sketch of the materials, as well as how much of the material they have available and the properties of that material. Engineers then come up with possible solutions for how the problem can be solved with the available materials. For example, engineers designing spacesuits would decide which materials they want to use and how they want to combine the materials in a way that is most insulating. They might decide on making the outer layer of the spacesuit white and reflective, so energy from the sun isn't absorbed by the suit. They may also decide to add a layer that doesn't release heat quickly. This will help the suit maintain its internal temperature. Engineers then diagram and build a prototype. A prototype is a scaled-down first draft of a technology. Once built, engineers test the prototype. They use the test to gather data about how well the prototype solves the problem during testing. Finally, engineers use their data to decide whether to refine or replicate. The data tell engineers whether their prototype technology solved the problem. Engineers designing a spacesuit would want to test how well their prototype maintained a specific temperature. Following an engineering process. Problem. Identify the problem, including the criteria and constraints of the problem, and summarize in 2 or 3 sentences. Research. Use what you know to help solve the problem. Record a minimum of 3 facts relevant to the problem. Survey available materials. List the available materials that can be used to solve the problem and include for each material a sketch, quantity, description, and properties. Possible solutions. List 3 ways the problem can be solved with available materials. Diagram and build prototype. Draw a hand-sized scientific diagram of the prototype solution you will then build from your materials. A scaled-down version of a technology is called a prototype. Title the diagram and include labels for each material or part of your prototype. Test. Test your prototype to see how well it solves the problem. Data. Collect data, measurements, and observations as evidence for how well the prototype solves the problem. Refine or replicate. Use your data to evaluate the success of the prototype and recommend if it should be refined or replicated. You may redesign your prototype to better solve the problem. Every conclusion must contain a minimum of 3 elements. 1. Restate the problem and describe the prototype technology. 2. Make a claim about whether the technology should be refined or replicated. 3. Use key points of data gathered from testing to support the recommendation to refine or replicate. Wow, I really learned a lot reading satellites, and I hope that you did too. I'll see you tomorrow with another one. Bye.